Yes. There has been a very astute observation that when I was making the calendar over winter break, scheduling an exam immediately after a break kind of takes away the, I just didn't have time to study. Because you do. Okay.
What if I go into the
Alright, let's look at it really fast. Okay. One mission, one goal, one perspective. If you remember the one mission, say it. Beautiful. If you remember the one goal, say it. If you remember the new thing, what's the one perspective? Life on loan. Okay? So, again, we're moving into an exam season. So, when you wake up every day and you don't want to study, whose breath are you wasting? Yours or God's? You know? Okay. So here's kind of what we're going to do. We're going to transition from the motivation that we built on the first lecture of Chapter 5 into a practical computational method here. So the key observation was that if we did have eigenvalues, especially corresponding to those diagonal entries, you force the existence of a free variable. That was like the main kind of climax of the last lecture. If you force the existence of a free variable, now you are no longer invertible, okay? And if you're not invertible, relate that all the way back to Chapter 3. There was something with determinants and not being invertible, and if that determinant is equal to 0. Okay, so we're relating those two things from each other across chapters. Determinant being 0 means you're not invertible, so that statement, not invertible, can also be logically equivalent to specific things with their eigenvalues, okay? So we'll take advantage of that and generalize it for Chapter 5. So we basically want to find, if the task is to find the eigenvalues of a matrix, then what I really want to do is I want to find all the possible scalars, lambda r, such that this specific matrix, the A minus lambda I, you recognize that from the previous lecture. So in case you don't know what is this coming from, watch the recording for the previous lecture and you'll know exactly where that comes from. And specifically, it's not just that this is a matrix equation. What was the condition that we put on this equation? If you remember. Exactly. So my it's not enough to say that I have the matrix equation. I need to clarify even further that with this matrix equation, it is guaranteed to have a non-trivial solution. And that's huge, because that was kind of the whole point of being able to make conclusions about whether or not it's invertible or not. Okay? All right, so let's see what that leads us to do. If we're trying to find these lambda values, if I am saying that this equation, which is a homogeneous equation, if this equation has a non-trivial solution, is this matrix right here, would we call it invertible or not invertible? It's not invertible. Why is it not invertible? Non-trivial solution. We basically supplied the very property that makes it not invertible, okay? So this lets me know that this matrix that I'm dealing with, the A minus lambda I, is not invertible. Does that make sense? If I want to find these scalars that satisfy this equation, in order that they have non-trivial solutions, I've just said I have a homogeneous equation that has not just the trivial solution, ergo not invertible. And if it's not invertible, then let's go, this is where we take our hop back to Chapter 3. So recall from Chapter 3. And that's going to let us know that then what our task really is we're trying to find lambdas such that the determinant of this matrix, which happens to be called A minus lambda I, the determinant of that matrix should be equal to what? If I want the matrix to not be invertible,
0.
The one value that makes that happen is 0. Because any other value of a determinant means that you actually can take the inverse of your matrix. So So does the logical progression make sense from what the question is asking and how all of these are equivalent reframeworking of the question? Yes? Okay. So this is a much easier problem to solve, we'll find, than just this. Okay? So we're going to tend to use these determinants. Here's a definition so that we can put language behind this. The scalar equation, which is basically this: the determinant of A minus lambda I is equal to 0. Because recall, determinants, they don't spit out vectors, they don't spit out matrices. A determinant is ultimately just a number, a scalar. This is called the characteristic equation. Characteristic equation. Of the matrix A. Now, characteristic equation should make everybody who has ever taken differential equations poke their heads out of the molehill, right? Right? Fascinating. Okay, so let's see. Now that we have a language for this, so instead of, if I'm asking to find eigenvalues of a matrix, what I'm really doing is I'm asking, can I solve for the lambda values satisfying a characteristic equation? Okay? It's a much easier problem to solve. So let's take a look at my example. In this case, the matrix A minus lambda I is the matrix, I copy and paste A, so 2, 3, 3 minus 6. And then lambda I is always going to be basically the identity, but instead of placing a 1, you place lambda, wherever 1 should be, so lambda 0, 0 lambda, and that's going to give me this lovely thing, 2 minus lambda, and 3, and then I have 3, and then minus 6 minus lambda. The most common mistake is kind of silly. You forget that you have to subtract the lambda. So if your entry is already negative, who cares? Just subtract the lambda, doesn't matter. And then, now we're told that this is the characteristic equation. The determinant of this matrix should be equal to 0. So the determinant of this matrix, which we now have that, so the determinant of my 2 minus lambda, 3 minus 6 minus lambda, this is supposed to be equal to 0, okay? Why do I want it to be equal to 0? Well, 2 reasons. That's literally the definition of characteristic equation. And then also because if the determinant is 0, that means that this is not invertible. If this isn't invertible, ta-da, that's got to be an eigenvalue, okay? This is a 2 by 2 because that's easy. For an example, we have 2 minus lambda times minus 6 minus lambda, and then minus 3 times 3 is just 9. Now, if you're rusty on algebra, it's time to not be rusty in algebra because that's going to be pretty painful. So minus 12, and then minus 2 of them plus 6 of them. So 4 of them. And then I have lambda squared minus 9. When I recoup, I have lambda squared for lambda. And then I have minus 12 minus 9, so overall minus 21, which now factors into lambda plus 7, lambda minus 3, which tells me that what are my eigenvalues?
Negative 7.
Ta-da! Each with a multiplicity of 1. Just observationally, how many eigenvalues do we have? What's the size of the original matrix? Purely coincidence, couldn't possibly have any meaning later, okay? Okay, is this make sense or no? So in general, that is going to be the way we want to do this. Let me write down a definition. So we have these definitions written down and stuff, right? Okay. because I want to keep the example up. And this is just some jargon that we'll use, that we'll want to be comfortable with. If A is an n by n matrix, n by n matrix, then the determinant of A minus lambda I is a polynomial, as we can see from the example, is a polynomial of degree, n. Like I said, 2 eigenvalues for a 2 by 2, entirely coincidental. Definitely doesn't matter whatsoever. Okay, so we have a polynomial, degree n, and then we call this the characteristic polynomial. Characteristic polynomial of A. What's the difference between the characteristic polynomial and the characteristic equation? Well, a characteristic polynomial is a polynomial, and a characteristic equation is an equation. There you go. In general, now we get we can formally define what we mean by multiplicity in this class. I'll put in parentheses here because it's technically the algebraic multiplicity, algebraic. You don't have to memorize that if you don't want. The multiplicity which is what we're defining, of an eigenvalue say lambda is its multiplicity as a root of the characteristic equation. Characteristic equation. Okay? Is this a circular definition? Close to. But what makes it not is because multiplicity for matrices and eigenvalues is a distinct concept from multiplicity of polynomial roots, which is something that I presume you have heard about in your Algebra 2 classes or college algebra. So that would be like if I had just in algebra x plus 4 to the 4th power times x minus 3 to the 7th power, then there's only 2 distinct roots, okay? There's only minus 4 and positive 3. So if we were listing out distinct roots, I would have minus 4 and positive 3. But in reality, multiplicity-wise, for the roots, I would say minus 4, minus 4, minus 4, minus 4. And then for this, 3, 3, 3 for 7, okay? For those of you who just took the Unit 2 differential equations exam, you kind of realize that that's super important, especially when doing those undetermined coefficients, okay? So it's the same thing. This is just multiplicity for eigenvalues, and we use the similar language. So what's the multiplicity of the eigenvalue minus 7? 1. What's the multiplicity for the eigenvalue 3?
1.
Cool. Let's extend the invertible matrix theorem. This time there's only 2 additions. But again, they're not really like true difficult additions to what we've already been talking about. They're more like summaries of the things that we've talked about. So hopefully, and I would encourage you to do this, especially for the final, is get a fresh sheet of paper just dedicated only to the invertible matrix theorem, A all the way down to, the end, so that it's not broken up in your notes. So continued. So because it's continued, those dots signify all of the previous stuff that we've already done. And then we're picking it up here in part S. So if the real number 0 is not an eigenvalue of my matrix, well, that's good news, right? Because this was the trouble child. We want to prevent 0 from being an eigenvalue, because if we did let it be an eigenvalue, then we make it not invertible by forcing the existence of a free variable. Okay? Does that make sense?
Yeah.
So if I want it to be invertible, I just take the opposite. So I say don't let 0 be an eigenvalue. And then part T is that we finally get around to saying it officially for the theorem. The determinant of A cannot be allowed to be 0 if we want it to be invertible. All right, so if I want it to be invertible, no can do, can't be 0. So the invertible matrices are allergic to these zeros. And there's no determinants, no eigenvalues. So again, that's not really new. You already knew that stuff. Now you know that it gets attached onto our invertible matrix theorem. I did want to leave a quick note here that's kind of helpful. In general, what it means to say that a scalar lambda is an eigenvalue of some n by n matrix. So of n by n matrix A. That's a logically equivalent statement to just saying that lambda satisfies the characteristic equation. The characteristic equation. Okay, what is that characteristic equation? Do you guys remember?
The determinant of A minus lambda I equals 0.
Yeah. So keep those two statements in your mind. If Pearson says, this is an eigenvalue, then you know that this has to be true. If it instead tells you something weird about a determinant of some A minus lambda I, and the error is like talking about eigenvalues, why are they talking about eigenvalues with this determinant? Well, it's because these are the same. So be able to go back and forth. Okay. Let me set up a new example here. So a little larger matrix, a little more applicable. Because honestly, the hardest part about this section is not doing the determinant, but just not forgetting how like algebra works in FOIL. So don't let that be the reason why you miss these. Even though it definitely will be. Find the characteristic equation. Oh, that is not how that word is spelled. Equation of, you know what I wish technology could do? I wish there was a way that I could like hold a device in my hand that as I speak words, it would just write it out. That would be pretty awesome. Although I would actually I would miss the feeling of tactile writing. Okay, let's set up a 4x4. So 5, 0, 0, 0, minus 2, 3, 0, 0, 6, minus 8, 5, 0, minus 1, 0, 4, 1. Okay, so immediately your brain should say, okay, well this is obviously an echelon form. This is a lovely, lovely triangular matrix. And why do I care so much about these, especially with eigenvalues? Well, because now, remember your determinant stuff. How do you take the determinants of triangular matrices?
Multiply down the
Yeah, just zip line down the diagonal. So you can see how that being a shortcut is going to take massive relevance now in chapter 5. Because if you have a square matrix and you have it in some sort of an echelon form, then this process of finding characteristic equations is quite literally tantamount to identifying diagonals and throwing them together as a polynomial. So it makes that correspondence really, really easy. So if I'm going to set up my determinant, right, because that's what I'm interested in, the determinant of this a minus lambda I, because I'm trying to figure out my characteristic equation. So all this means is the only thing that's going to change, you copy and paste your matrix, and then just put minus lambda on all of the diagonal entries, and bingo, you have a minus lambda I, okay? So here is 5. Is 5 a diagonal entry?
Yes.
Okay, so I put minus lambda. Is 0 a diagonal entry?
No.
Frankly, are any of these below a diagonal? Okay, so do they get changed?
No.
So copy, paste. Okay, is that minus 2 on the diagonal?
No.
What do we do with it?
Leave it the
Copy,
same.
paste. What about the 3?
It's on the diagonal.
Okay, so what's the only modification I made?
Minus lambda.
What about anything else?
No.
Copy, paste. 0, 0, 6, minus 8, 5 minus lambda, 0, minus 1, 0, 4, 1 minus lambda. Okay? So now, you don't have to be super tedious and like expand out a minus lambda 0, 0, 0, 0 lambda blah, blah, blah. You don't have to do any of that because this isn't supposed to be hard. Copy and paste your matrix, put minus lambda on the diagonal, okay? Now, this is now a determinant question, and do we still have a triangular matrix?
Yeah.
What? That's crazy, because what can we do with this? Just go down the diagonal. So I have 5 minus lambda times 3 minus lambda times 5 minus lambda and 1 minus lambda. Ta-da! Okay, so that's why we care about these. Now, we can simplify this a little bit, right? There's 2 of these 5 minus lambdas, so I'll square it. And then we have 3 minus lambda and 1 minus lambda. So this is a totally acceptable way to write that equation. I'm going to provide OR here for my fellow OCD math people. And you like to see the lambda come first. We can do lambda minus 5. The reason we're allowed to switch that is because it's squared. Ergo, the sign doesn't matter of the inside here. And then these are both backwards, meaning that if I reverse this one and then also reverse this one, I am multiplying by -1 and -1. And -1 times -1 gets me back, so I don't change my polynomial if I make sure to flip both of these to have the lambda leading term. Again, super optional, but this makes me happy and this one doesn't. That's the only difference. Okay. So, eigenvalues. Talk to me. What are the eigenvalues of A? Based off of this.
5, 3,
5
multiplicity 2, 3, 1.
That was the most disheveled, disorganized class response I'm going to say.
5, 3, 1.
5, 5, 3, 1. So notice that this equation gives that to me straight up. What could I have done this entire time?
Just go down.
5, 3, 5, 1. That information was already given to you. Ah, I got him. No, okay. So I promise I did not just teach you an entire section to waste your time. This will become useful for diagonalization, okay? But this is my way of getting you to review 5.1 without you realizing it, okay? So you could choose to, you can get that information either way. And the only reason that works, though, is because this is a very specific type of matrix. It is a what?
Triangular.
Okay, so if this weren't triangular, would that have corresponded perfectly? No. Okay. Again, multiplicity of this 5 is 2, so we keep note of that. I would not want to say, so here's what you would not want to say. Do not say, that you have 5, 3, 1, therefore you have 3 eigenvalues.
Yeah, 4 eigenvalues. What, Scott?
Was that a serious
No.
Okay. Okay. Do we see why you don't want to conclude that this matrix has 3 eigenvalues?
That's
Because there's 4.
It's like a massive problem. Remember the first example when we had 2 eigenvalues and it was a 2 by 2? Right? Is 3 equal to 4?
No.
No. Okay? So what's really going on here is there's that multiplicity, okay? Of 5 for the fourth one. Okay. Are we happy with this? Are we? Oh, that's right. That's right. Okay. So we're quite chummy with this stuff. Let's do another example. Just get some more examples for repetition. Okay, so if the characteristic polynomial, so I'm going to give you a characteristic polynomial specifically for a 6 by 6 matrix. So a 6 by 6 matrix has a characteristic polynomial of lambda to the 6th power minus 4 lambda to the 5th minus 12 lambda to the 4th. And so I think to myself, if I want to find the eigenvalues, so find the eigenvalues, and also obviously their multiplicities. Well, let's do that. So what this is trying to get you to do is recognize that all of your skill with manipulating and factoring polynomials is still applicable here to characteristic equation stuff. Okay? So the way you would intuitively factor this, well, I have 4 of those, so I'll factor those out, and I'm left with 2 here from this, then minus 4 lambda, so 5, take out 4 of them, and then I'm stuck with just 12 there. But this in itself is really easy to factor, right? That's just, so it's a negative, so I need the 6 is greater than the negative sign, minus 6. Because it's 6 times 2, but this one is negative. This is a negative version, so I need this one to have a bigger contribution, negative. And then I say, okay, fantastic. So this basically gives me my information. I just read it. If I were to list out the eigenvalues, I would have what?
6 and -2.
Okay, yes. So I have,
6 and -2.
I would have, we'll start, so what does this give me?
0.
0.
Jessica, you want to say that louder for everybody?
0, 0, 0, 0.
Why, Jessica, did you repeat the same number 4 times?
Because it's multiplied 4 times.
Oh my goodness, the multiplicity is 4, okay?
Whoa.
Alright, what about this one?
It's not.
6.
6.
And what about this one?
-2.
Okay, so how many eigenvalues do we have?
6.
So everything is happy and good with the universe. We have the same number of eigenvalues as our size of the matrix. What we would not say, okay, so what we would not
What I
say is that we have 0, -2, and 6, and so therefore we only have 3 eigenvalues.
No, that's a bad answer. No, there's just 2 though.
Okay? This is bad. Don't say that. We have 6. Okay. Alrighty. So let's now do another definition. So why, really what are these characteristic equations storing? That's a good question. Thanks for asking. And so the characteristic equations are storing information about the original matrix. Okay? Because we might ask, is it possible for 2 different matrices to actually have the same characteristic equation? Because when you think about just the word characteristic itself, like a character, right? A character is distinguished from other characters. So other things, types of characters, protagonist, antagonist. Every single antagonist you've ever watched in every single movie is not the same dude who just appears as the cameo as, hello, I am the antagonist. Okay? So you won't be watching like the Chronicles of Narnia, and then instead of it being the White Witch, it's just the antagonist, okay? So it's filling in a character, but it's different. It's unique for every single context. So in the same way, matrices, they don't have to be the same exact thing in order to be characteristically the same, okay? So we're going to talk about them being similar. This is going to be our new math word. And in another reason to be obnoxious to your non-STEM friends by nitpicking their vocabulary, okay? So if A and B are n by n matrices, then A is similar to B. Really profound stuff, I know. If there exists some invertible matrix P such that P inverse times A times P is equal to B. Or, we could also equivalently think of this equivalently. If I want to think about this, A being P times B and P inverse. Either way, we call A and B similar and changing A into P inverse AP is called similarity transformation. That's not how that's spelled. Transformation. Okay. Exist invertible matrix P such that P inverse AP is B. So notice that this isn't saying that A is just the same matrix as B, but rather if you had some matrix that's invertible, and you take its inverse, left multiply it, do my matrix A, and then effectively undo, with the regular version, if that gets you to B, we call those similar. Okay. Let me put up a theorem, because otherwise this doesn't make any sense. This is the following theorem is the linear algebra chapter 5 equivalent to debunking I'm not like other girls, but for matrices.
Wow. This is another marriage counseling.
Saying another marriage counseling on a math lecture is kind of crazy work, then no.
You're welcome.
I don't know, was it counseling or was it just math advice?
I'd probably counseling.
Counseling implies that you worked toward a solution, but we didn't just work toward a solution, but we just simply proved that there is a problem. That would be like a counselor who goes to somebody who's broken
We did prove the solution.
and proving that they are in fact broken.
Can you give examples to prove your solution?
Okay, so if I have two similar matrices, then here's why we care. They have the same characteristic polynomial. Characteristic polynomial. Polynomial. And if they have the same characteristic polynomials, even further, and hence the same what? What might we care about that this entire chapter is kind of titled?
Eigenvalue.
Yeah. Eigenvalues. And even further, not just the same eigenvalues, but preserving their multiplicities as well. With the same multiplicities. Now that might not feel super profound until we step back to originally what the definition of an eigenvalue even was, right? These eigenvalues are the very scalars that basically tell us, hey, if I take a vector and then transform that vector using my matrix A, but that output is really just a scaled version of my original input. Now if I have two completely distinct transformations from each other that are similar, so what they do to the space transforms them differently, yet preserving effectively the eigenvalues. In other words, those specific scaling amounts are going to be the same. So even though the transformation might accomplish something different from each other, they still fall under the same category of preserving the space similarly. Okay? I unfortunately cannot draw three-dimensional motion animation things on a whiteboard. But Jesse, no. There is an excellent video done by 3 blue, 1 brown. And you know what this nerd did? He put in a program to make it visualize and animate precisely all of this stuff.
Let's
Okay?
go.
So if you're more of a visual learner, you really want to see what's actually happening with the transformation, his video on the eigenstuffs is going to be super helpful for you. Okay? Okay. So let's see what time it is. Wow, would you look at that? There's enough time to do a new proof. Okay. Okay, so let's actually prove question.
Student crew was like
We're gonna need some similar matrices to start. Let A and B be similar. N by N matrices. Why am I allowed to do that? Well, because the theorem is saying start with similar matrices. You don't have to prove that they are to start with. The theorem is stating that if we start there, we're allowed to assume the starting position. So AB similar NBN matrices. Okay, so since, here's a definitional observation. Since A and B are similar, right, think about the definition. So if you wrote down the definition, flip back in your notes, and you'll realize that all I'm doing is restating the definition. There exists an invertible matrix P such that A is equal to PB, P inverse. Again, have I really done anything new to the proof? No. I've simply stated that they are similar, and if they are similar, this is just a restatement of that definition. Okay? Okay, so now let's articulate the task. So what do I want to show? I want to show that A and B have what? What am I trying to show in the theorem? Yeah, same eigenvalues, but mainly same characteristic polynomial, right? Have the same characteristic polynomial. Okay, what does it mean for them to have the same characteristic polynomial? That requires us to remember the definition of characteristic polynomial in the first place. So flip back even further in your notes to where we did that definition, and you'll see that all I'm going to do is reproduce that definition. That is, the determinant of A minus lambda I should be the same exact thing as the determinant of what? Yeah. This is the characteristic polynomial of A by definition. This is the characteristic polynomial of B by definition. So if I'm trying to say that they're the same thing, all I'm doing is this equation right here. Not crazy, nothing crazy. Okay, so here's my anchor. If A is PVP inverse, I'm reminding myself of that definitional thing that I can do. then the following are all going to follow logically. Okay? So A minus lambda I, A is equal to PBP inverse. So I'm going to substitute PBP inverse for A. PBP inverse. That is now A. Minus lambda times, now here's the thing. This is the non-trivial step that I wouldn't necessarily assume you could figure, well, I mean, you could probably figure it out. But I'm telling you, so what's a clever way to represent the identity here in relation to P and P inverse?
PP inverse.
Yes, and I want to do it that in that order.
Don't you put
P times P inverse.
for just me? Can I just put I then put the second step again?
I would,
Prove.
in terms of this section, this is pretty much symbol for symbol.
Oh.
Yeah, there's not too much room for freedom in this section. You can reword how you want some of that, but when it gets down to this is just a straight manipulation. And why might I want to view my I as P inverse? Well, because I can do some factorization.
Yeah.
Remember when we definitely all memorized the algebraic properties? The left distribution lets me take P out. So BP inverse minus the lambda with P inverse. Okay? So I've taken left distribution of P to the left. That's why the order here matters. If you had done P inverse in front of P, this doesn't really work. You can't factor to the left. And then what's the other thing I can factor out of here? Which direction must I factor it? To the right. Because it's on the right. So remember that in general, you cannot say that AB is BA with matrices. So that's why I'm being super specific about this being left distribution versus right distribution. So now we're left with P, and we just need to be careful in parentheses here, because it's not lambda standing alone, because lambda is a scalar. So how do we accommodate that when lambda is in the mix of all these matrices? Yeah, lambda I. Which, friendly face, right? Okay, and then P inverse. Okay. You can already probably see exactly where this is going. So then, by the multiplicative property, of determinants, which, reminder, that is from chapter 3. I have that so notice that this is what the equation is accomplishing. I am relating A minus lambda I to B minus lambda I with this P inverse business, right? Then I have, if I now take the determinant of both sides of this equation, A minus lambda I is equal to the determinant of that whole thing. I'm going to use the hard bracket, not because I'm indicating that there's a matrix, but because when you have multiple nested parentheses, it can be helpful to use a bracket to distinguish. P B minus lambda I times P inverse, all in the determinant there. And then that multiplicative property is letting me basically say the determinant of each individual matrix multiplied together. So this is really just the determinant of P taken as its own multiplied by the determinant of B minus lambda I taken on its own multiplied by the determinant of P inverse taken on its own. So that splitting up is a direct citation of this property of determinants here. And then, if I've done that, notice that as soon as I've expressed them as these separate chunks, each one of those is really just a really chunky way to describe a scalar value. This is a scalar times a scalar times a scalar. And now I have scalars multiplied together. I can rearrange the order conveniently. So I'm going to put these together. I want to have my determinant for P multiplied by my determinant for P inverse, like that. And I have my determinant over here still hanging out for B minus lambda I. The reason I care about this is because I'm going to use this multiplicative property in reverse now to get P and P inverse back together, okay? So I could have the determinant of P and P inverse now multiplied back together again. Determinant of B minus lambda I. Now, the more astute of you are probably like, well, that is the most roundabout possible way. Why couldn't I have just rearranged it inside, right? Because that's sure what it seems like I'm doing. But notice that in general, you're not allowed to assume that it's commutative. So just because it happens to conveniently work out this way does not mean you should shortcut your proof and do something algebraically illegal, even if it gets you to the same thing. I should not just assume I can commute P inverse with my B minus lambda I. Do not do that. If I see that in the proof, well, that's kind of game over, because that tells me you don't even know the rules of how matrices work, okay? So just because it ends up looking like this does not mean that it's a legal rule to flip those out of convenience. Yeah?
Isn't the determinant of P, P1, P determinant of P inverse just 1?
Yeah, because this is the determinant of the identity. Yeah. Very, very, very good. Let him cook, as they say. The determinant of I, B minus lambda I, which, like he just said, is 1 times the determinant of B minus lambda I, which, fun fact, 1 times anything doesn't change anything, so I have the determinant of B minus lambda I. That is effectively what I'm trying to show. Because this is the same exact polynomial. Yeah?
How would you show that through, like, just the times 1 part? Actually, never mind. That's a good example.
Okay. Let's see. There was a.
This is just 100%
There's only one thing that could make this proof even more complete, actually. There we go. Honestly, if you put perchance instead of a box to end your proof, I wouldn't even be mad.
If you put like a box with a squiggly through it and a happy face, would you mark points down?
No, if anything, I might give it extra.
Really?
No, that was a joke for legal reasons. That was a joke, but.
If we pause the recording.
Okay, questions about this theorem or and proof? Anything related to? Because when I tell you, I really love this theorem and proof. Like emotionally close, warm, dear to my heart. Yes.
Just wondering 2 things. So like, I might have just missed the point in class where you could multiply, like put the determinant P time, well, the part in class where determinant P times determinant P inverse can equal determinant P inverse.
So are you asking what if I want to go the other way? Because there are technically 2 alternate definitions.
What-
Checks out if you do the algebra right.
No, I meant like, yeah, actually, sure. And then, how would you prove, like, I don't know if it's discrete or topology, I really don't know, but like, how can you prove that 1 times something always equals itself?
That is something you don't prove, and rather you cite the existence of the identity axiom in fields.
What is a density axiom?
Well, go back to chapter 1, and it's all of those lists of field axioms. Commutativity of addition, associativity of addition, 0 is the identity for addition, 1 is the identity for multiplication, etc., etc., etc. So those are just properties. We don't really have to prove those. Any other questions?
Now, this is Q proof.
Questions, comments, or concerns? Any other contributions to the whiteboard?
Cursive. RAR.
No.
Perchance squared.
You guys do like 10
Ooh,
more
I got
times.
one.
All right, you guys are dismissed.